Welcome back to another hands-on Kafka Connect exercise. This time, we'll learn how to run and maintain a self-managed connector with Confluent Cloud. Before we get started, there's a bit of preparation that you should take care of to make sure you have all of the tools you'll need to be successful with this exercise. If you don't already have a Confluent Cloud account, make sure you do so now. And also take the time to complete the necessary environment setup steps. As mentioned previously in this course, the rate at which fully managed connectors are being added to Confluent Cloud is pretty impressive. But it is possible that the connector you want to use with your Confluent Cloud cluster isn't yet available. In this scenario, you'll need to run your own Kafka Connect worker that will connect to Confluent Cloud. In this exercise, we'll be doing exactly that. We'll start off by establishing a self-managed Kafka Connect cluster that will run in Docker containers and will be configured to write to and read from Kafka topics in our KC101 Confluent Cloud cluster. Next, we'll create a number of Kafka Connect data pipelines. The first pipeline will use a self-managed Debezium MySQL source connector to stream data from our local MySQL database into a Kafka topic in Confluent Cloud. The second pipeline will use a self-managed Elasticsearch sync connector to stream data from a Kafka topic in our KC101 Confluent Cloud cluster to a local instance of Elasticsearch. A third and final pipeline will use a self-managed Neo4j sync connector to stream data from a Kafka topic in our KC101 Confluent Cloud cluster to a local instance of Neo4j. Our self-managed Kafka Connect cluster will require the Confluent Cloud Java configuration settings we previously obtained. We'll make these settings available via environment variables using the env-delta file that was created in the exercise setup steps. Before we do this, though, let's review the contents of the Java config file. Observe that the settings include the Confluent Cloud cluster endpoint that is used for the Bootstrap service property. It also includes values for the cluster API key and secret, which clients need to authenticate with Confluent Cloud. The settings also include the schema registry endpoint and API key and secret. These are also needed by the clients. Next, let's review the contents of the env-delta file. As you can see, this file contains a number of export commands that create environment variables set to the value of a corresponding Java client configuration setting. We'll be establishing these variables for our current command shell. As always, we should verify that the previous step was successful. You should see in the command output that the environment variables contained in env-delta are active. Now, let's examine the Docker container definitions being used by the exercise environment. The first Docker container, named Connect1, is one of the two Kafka Connect worker nodes we will be working with. Let's take time to examine some of the configuration settings that are specified in the container's environment settings. On line 15, we see that connect bootstrap servers is set equal to the environment variable bootstrap servers. This is the endpoint address of the KC101 Confluent Cloud cluster. Line 16 contains the group ID property, which is set to KC101. This is what tells the Connect1 worker node which Connect cluster it should join upon startup. All other worker nodes with the same group ID value belong to the same Connect cluster. Lines 17 through 19 contain three internal topics the worker nodes use to keep in sync with one another. The names for these topics need to be unique for each Connect cluster. Next up, on lines 29 through 31, you'll see three more environment variables which set values used by the Connect workers to connect to schema registry, which in our case is located in Confluent Cloud. The workers and underlying producers and consumers will use lines 46, 51, and 56 to authenticate with the Confluent Cloud cluster. On lines 64 through 67, we see that the connector plugins that we'll be using during our exercises are being downloaded from Confluent Hub and installed on the Connect1 worker node. The Connect2 worker node container configuration also includes these same plugin installation steps. Connector plugins must be installed on every node in the Connect cluster. Scrolling down, we'll find the environment variables are also used to define the Connect2 worker node. Scrolling down further, you'll see additional Docker containers defined, including MySQL, Elasticsearch, Kibana, Neo4j, and Kafka Cat. Let's now start the Kafka Connect cluster as well as the other Docker containers. And of course, we'll verify the containers are running. And finally, we should check that the Connect workers are ready and that the Elasticsearch, Debezium, and Neo4j connector plugins are available. Let's now verify that our self-managed Kafka Connect cluster is using our Confluent Cloud cluster. Observe there is a consumer for each of the internal topics. Next, we'll stream data from our local MySQL database to a Confluent Cloud Kafka topic using the Debezium MySQL source connector. We'll start by viewing a sample of records in the database. These are the records that we'll stream to a Kafka topic in Confluent Cloud. But before we continue, let's start a process to generate additional rows to the MySQL database. When that's done, we can create the MySQL source connector instance. And as always, it's a good idea to check the status of the connector instance. Once it's up and running, we can observe the records that are being written to the Kafka topic by the MySQL source connector. Before continuing, let's stop the MySQL data generator that we have running. Our next step in this exercise is to stream the data that was sourced from the MySQL database to an Elasticsearch sink. To start, we'll create an Elasticsearch sink connector instance. Notice that for this connector, we set tasks max equal to 2. This is primarily for instructional purposes, since the load doesn't really need to be spread out across our 2 Connect worker nodes. We'll examine how these multiple tasks are distributed in later exercises for the Kafka Connect REST API and troubleshooting modules. Again, we should check the status of the connector instance. With it running, let's inspect the data that is written to Elasticsearch. Our next step in this exercise is to stream the data that was sourced from the MySQL database to a Neo4j sink. Notice again that for this connector, we set tasks max equal to 2. Let's check the status of the connector instance again. Everything looks good. All right, let's take a moment to review what we've achieved up until this point. So far in this exercise, we implemented a self-managed Kafka Connect cluster and associated it with a Confluent Cloud cluster. We created a source connector instance that consumed records from a local MySQL database and wrote corresponding records to a Kafka topic in the Confluent Cloud cluster. And we also created 2 sink connector instances that consumed records from a Kafka topic in the Confluent Cloud cluster and wrote corresponding records out to a local Elasticsearch instance and a local Neo4j instance. If you're running this demonstration yourself, you'll need to tear down the environment after doing so to avoid unnecessarily accruing cost to the point your promotional credits are exhausted. And with that, now you have everything you need to run a self-managed Kafka Connect cluster with your own Confluent Cloud instance.